In this video, we're going to walk through the MagicGrid Book of Knowledge version 1 that you see on the left and version 2 that you see on the right at the same time. We're going to explain how they're the same and how they're different, and we'll remember that MagicGrid is a methodology. This methodology can be used with any of the SysML language tools, such as Cameo, Magicdraw, Rhapsody, etc. So it's tool agnostic as long as you're using the language SysML. We can get both of these documents from a quick Google search, and they are downloadable. So now we'll get started. We've got the contents, the foreword, the reviewers, and the preface, which will explain why MagicGrid. And we've got the same situation here. So the reason that we're going to use MagicGrid is it's compatible with vanilla SysML, no extensions are required. It clearly defines the modeling process, and it's tool independent. Now we'll look at the MagicGrid itself that you're seeing here. Both of these are going to be the main navigation page or the index of all of the process that we're going to follow. So we're going to attach hyperlinks to each of these cells as we complete the MagicGrid, and the cells hyperlinks are going to go to different diagrams, tables, or matrices that are going to help describe what the contents of that cell. So in general, we're going to work top to bottom, left to right. The key similarities between V1 and V2 is that we have 3 different domains: the problem domain, the solution domain, and the implementation domain. So problem domain, solution domain, implementation domain. And basically we're going to work the problem domain to wrap our hands around the problem. This is your conceptual phase, the top. And then we're going to work through logical solutions. So this is the logical domain. And then we're going to work on the physical implementation, which is the implementation domain. So those are the similarities. The differences is the pillars. The 2 and 3, the behavior and structure pillars, have been flip-flopped from version 1 to version 2. We'll notice that it goes behavior then structure on version 1, and then structure and then behavior on version 2. So as we go through this documentation, we're going to have to remember that throughout. But that is the primary difference. Also, we have this safety and reliability column here. There's information about the safety and reliability pillar in the appendix, but the main example is not going to go into great detail about this pillar. We see that the vehicle climate control system is going to be our case studied system of interest for both V1 and V2. It's showing here the different domains. Here's our case study. You'll see it's the same. And then we jump into the problem domain, which is going to be these first 2 columns of the MagicGrid. So first we'll start with the black box perspective, identify the stakeholder needs, creating requirements within a requirements table, explaining how to import requirements into Cameo. That part is specific to Cameo, obviously. Show you how to nest requirements within requirements. So we see that this one has a little bit more detail. There's more requirements than this one. So that's going to be like a common theme throughout, is that V2 has a little bit more detail. So now we're going to create the system context, some of the structure within our black box problem domain. So now we'll see the package structure for the first time compared. You'll note that we have the problem domain and then the black box. So problem domain just means the first domain. That's why it says 1 there. And then 1 black box is the first row in that first domain. And then it talks about 1 stakeholder needs. So 1 is going to be the first column. 3 is going to be the third column, because this is version 1. Version 2 we're going to have the same thing, problem domain, first row in that first domain. Stakeholder needs is still column 1, but the structure column is column 2. So this tutorial in both of the MagicGrid versions are going to explain how to create the IBD and the flows across, add the fancy icons, everything that needs to be done for this diagram. So here are the instructions here. And now we'll go to use cases. So we start with our use case and then we refine it with an activity diagram, which will then be put into swim lanes. So all of our actions are going to be associated with elements of structure. These elements of structure are the elements that we have conceptually created before. And here is V1's activity diagram, and V2's is just a little bit more complex. Again, you'll note 2 use cases, 3 use cases, 3 system contexts, 2 system contexts. That's because the columns have been swapped in the original index MagicGrid. This is going over how to create the use case. And how to create the activity diagram, add the actions, add the swim lanes. So that was a tutorial. So the next step is going to be measures of effectiveness. And that's what we see on both. And what we're going to do is create this block called measures of effectiveness holder, and we can add our value properties that are going to be our measures of effectiveness, and then we take our main conceptual block from our problem domain and create a generalization relationship to our measures of effectiveness holder. What that's going to do is allow the value properties or measures of effectiveness to be inherited by the climate control unit or our system of interest created in our problem domain. So that's what you're seeing here. This little up caret is the is inherited. That's what that caret means, and so it's hidden by default, but there's some instructions on how to change that setting. It's explaining right here how to add value types to the value properties. So like sound level is going to be of type decibel. The total mass is going to be of type mass, or like mass kilogram, so it could have a unit associated as well. Now it is showing us the white box perspective, and we are now going to start recognizing that we have the structure and the behavior and different levels of abstraction. So the system context level is right here where we have our use case and our system context block. So this is the most abstract, and then we jump down to the system of interest level where we have the user and the system of interest, and then we can jump down. That icon is a fork, which allows you to look into more depth. So now we're at the 2 is the system level, 3 is going to be the subsystem level, where we are showing subsystems within our system. And then we've got what some would call the component level, and it goes on and on and on. So you could Russian doll this into any number of levels. But for this example, we're going to stop at 4. So now we're going to talk about the functional analysis. So that is this cell within both grids, So that means that we have already completed this black box row, and now we are on the white box row of the grid. I think one thing that's important to note is that this process, the problem domain process, you're going to have the block, the system of interest block. It's going to live within the black box containment tree location. But when you jump from black box to white box, you're going to actually move that original system of interest block from the black box location in the containment tree to its new white box location within the containment tree. So depending on what step in the process that you are within the problem domain is going to tell you where your system of interest block should live. So moving forward, we're just going to be figuring out how to complete these 4 cells in both of the magic grids. Note that they're not exactly in the same order, so we're just going to have to work with that. So this is giving more detail or refinement from use case to activity to more detailed activity. So we can just zoom in using that rake icon. And we're going to be adding more detail from a behavioral perspective that you see here. And we've got our structural perspective that we see here. So now that we created our structure, we're going to create our internal block diagram, which will explain how to connect the subsystems together. And we also do that here. We've created our block definition, which is similar to this. And then we're going to add our internal block diagram. Note that these IBDs that you see are going to have subsystems as the part properties that are shown. And so therefore the frame of the diagram is the system. So it's a white box of the system block. What we did before was a white box of the system context. Therefore we could see the system as one of our part properties. So we're down one level, added one more level of detail. So moving forward, it's going to show us how to type the proxy ports and create the interface blocks and where to put those in the containment tree, and create some tables to show the ports that we've created. On the left, we're showing how to refine or connect the requirements from the user needs to specific activities. And on the right, we're talking about the measures of effectiveness at the subsystem level. So we can either create a new MOE holder, or we can use the same one and add more detail to it. But the thing that we're doing here is we are now connecting our subsystem blocks, cooling, heating, etc., with a generalization relationship to the MOE holder. This is how to show the caret that I was talking about earlier. This is the show inherited setting that you can set to true to then show that little caret. So now you have completed the problem domain, because you have completed all of the cells of the black box and the white box. So before we start the solution domain, we'll kind of explain that the problem domain could be completed by one team or organization and then provided to several different other organizations to then gather their specific solutions. So this could be the solution of contractor A, this could be the solution of contractor B and C. So, they could use, contractor A, B, and C could use problem domain that is from the supplier to be able to complete their respective solutions. So that's why the blocks from the problem domain are not then dragged to the solution domain. These are different packages in this case, but can be different models. Note that in this example, we will only be going through one solution, so everything that you're seeing going forward is going to be within one solution. It explains how to deploy the solution domain. It also states that you can have magic grids nested within magic grids. That is acceptable. So if you had different teams that are working at the subsystem level, for example, they could go through the whole magic grid structure itself at their respective levels. So their system of interest would be the subsystem. So you could nest magic grids within magic grids. This is going to be used in super complex systems that require teams and teams and teams of expertise to complete. For this example, we will not be doing the nested magic grid. We should also note that every single one of these magic grids would be its own project. So you could use other magic grid projects to be able to create this nested structure. This example that we're going through is not going to use nested magic grids, but it is important to understand that it can be done. So this right here is just showing all the packages that you would see within one solution domain. So this is what we're going to be working through. We have a more detailed view of our requirements that's going to be at the VCC requirements level instead of the abstract user needs level, and then we would connect the requirements together using a derived requirement linkage. You can see the same thing for V2. You can put these requirements in a matrix and then connect requirements to other element types such as value properties, blocks, elements of structure, activities, elements of behavior, using the refine relationship. So now that we've done the requirements, we can start building out the system structure, so the logical structure within the solution domain. And we can see that here. We can start to connect elements from the logical domain to the conceptual domain, or the solution domain to the problem domain, using the abstraction relationship. You can also show the same exact relationship on a BDD using the abstraction relationship between solution domain and problem domain. This is a custom legend which is going to highlight any element that is within the problem domain package, and this is the same for the solution domain package. Both views are acceptable. In most cases, it makes more sense to use the matrix. MagicGrid is explaining these exchange items, whether they are blocks or signals, and creating taxonomies for them. It also explains the proxy ports that are typed by interface blocks, and the is conjugated, which is that little tilde right there, which changes the direction of the arrow, and where they live in the containment tree. We're capturing the logical subsystems, establishing traceability to the problem domain model. Here we have the abstraction relationship, connecting the solution to problem domain. Now we have completed the system structure for V2. Got a tutorial on how to create the structure for V1, which is going to be similar to what we just looked at. This is a little bit different from V2. We have this cooling system design that has a generalization relationship to cooling system. To understand this relationship, we need to look at the containment tree. We have the cooling system right here and the cooling system design down here. The cooling system design is going to be the white box block, which means that you can see the inner workings of the cooling system. The cooling system block that is living within the system structure is the black box version of this, and that means that you're only going to see the ports and nothing internal to the cooling system on this block. So when you have that generalization relationship, you are going to, the cooling system design is going to inherit all of the ports that have been created on the cooling system block. So that is how it works for V1. V2 is the same exact thing, except for they've changed the terminology from cooling system design, so the word design, to cooling system architecture. But other than that, it's the same, has the same package structure. The thing that I would have chosen would just be calling it cooling system white box and cooling system black box. I think that's way more understandable. Going back to where we were in the walkthrough, we're going to continue down this tutorial. And then we get to the subsystem behavior and the system behavior. So now we start to have a state machine. The state machine is going to have nested activities within it. So the activities can be added to the entry, do, and exit behaviors of these states. So in this case, we're adding it to the do, initializing system components. When it gets to that step, it's going to do this activity. Something interesting to notice is that after you have created your structure for your subsystems that live within your to solution domain, that is the black box, you would then create the white box 2.1 subsystem package structure. Only in here, the white box view of the subsystems, are you going to create behavior. There is no behavior that is created within the to solution domain. We can see that if we go over to the version 2, and it has the solution domain that's been feathered out, and we see that we have 1 system requirements, 2 system structure. There is no 3 behavior at all. The behavior is going to be captured within the white box of the subsystems. Going back to where we were in the walkthrough, we're going to then go through this tutorial for creating the state machine and adding triggers and signals and activity diagrams to the state machine. Right here, we're modeling the structure and IVDs. And on the right, we have the MOE holder, and we're connecting that to our VCCS, and we start to add constraints. So we've created parametric diagrams to help us do the math for us. We then can create a satisfy relationship between a value property to a requirement, and we can create a refine relationship from the constraint to the requirement. We then can create linkages between the solution domain to the problem domain, as you see here. And we can refine values for our measures of effectiveness or any of our value properties within this properties pop-up. This is running it in simulation and being able to calculate the kilowatt hour total energy . and you're seeing some more examples of simulation and creating instances to be able to capture some of these values at a specific snapshot in time. And the red green is going to say if it passed or did not pass the requirement that it was attached to. This is what we saw earlier, which is decomposing the system. And we have our configuration and our constraint. So a lot of the same that we just walked through. Now, we saw the traceability to system requirements right here. So you're creating linkages between part properties, constraints, value properties, ports, etc. to the requirements. We got satisfy linkages. So V1 is going to go straight to the implementation domain, while V2 is going to give us some more information on how to build out these subsystems right here. And yeah, it will show us this how to create the 2.1, 2.2, 2.x, all different subsystem package structure and relationships and requirements, etc. This diagram here is showing the generalization relationship between the cooling system architecture to the cooling system, and it's going to capture the internal block diagram and show you where to put the cooling system architecture block within the package structure that we talked about before. So we got the cooling system architecture, which is the white box, and the cooling system black box. And we can redefine the ports. And now we can add the subsystems within the cooling system. So this is the white box. You've got all of the parts that are within it. While this cooling system up here, you don't have any parts. Now we're going down and explaining how the cooling system's parts are connected using an IVD. Now we're looking at the interfaces used and adding item flows. Now it's going to talk about the subsystem behavior. Remember, we said that the behavior is not captured in the black box system level in the solution architecture. It's not captured in this level right here. It's actually captured within the subsystem. So it walks through how to do that and run it in simulation. Now it's going through the subsystem parameters and adding the relationship to the MOE holder. This is all very consistent with the process that we've done before, so it should seem familiar at this point. Now we're adding some traceability to requirements at the subsystem white box level. So the next thing to do is to build a configuration of the model. So you might ask, how is the system configuration different from the solution domain that we just built out? And the answer to that is the architecture is slightly different where these generalization relationships lie. So within the solution domain, we have a white box built out subsystem 1, architecture 1, with a generalization relationship to the subsystem 1. And we would do the same for all of our different parts or subsystems within our model. So, and then our system block has a subsystem 1, a subsystem 2, and a subsystem 3. So that's how the solution domain works. If we scroll down to how the configuration domain works, we have VCCS configuration is a type of VCCS, and that's at the system level. So what we're doing is we're going up a level. So we're saying that this specific configuration is a type of this system, and this system has this specific cooling system and this specific CP system. So, and it's redefining cooling and redefining CP. The difference is that the generalization relationship is at the system level versus the subsystem level. Some things to note: we do not see the configuration domain within the MagicGrid itself in either version 1 or version 2's MagicGrid. It does show up in the containment tree. If we scroll back up, we can see that it shows up as 3 configuration domain within version 2. The configuration domain is not mentioned at all in version 1 of the MagicGrid. Additionally, the configuration domain was likely created to be able to show different variants or obviously configurations of a system and be able to do trade studies between different solutions with their specific configurations to like other organizations' systems with their configurations. So it's a way to just specify even more what the exact variant and configuration would be. It goes on to show us how to build the configuration in great detail from a structural and behavioral standpoint, and shows us right here the parameters, so our parametric diagrams, how to create those, how to redefine those, etc. So now we have the implementation domain, which is the final domain that you see down here, and this is going to be the physical aspect and not the logical or conceptual as we've created now before. And we'll note that you start doing the same process where you do the requirements, break them down from stakeholder needs to system requirements to physical requirements, and we have that's it. That's all it shows in version 1. And version 2 is also very sparse. That's all the information it tells us about the implementation domain. The reason is that there's many different ways to build out the physical architecture, and so MagicGrid doesn't specify the way to do it. That may be done in future MagicGrids, but not yet. So MagicGrid version 1 just goes into some glossary and other information, and that's it. And then MagicGrid version 2, now it has this appendix which is going to tell you about the safety and reliability. Remember the last column on the right side of the grid, and give you some information on how to incorporate all of the reliability studies. So that's what this is here. And then we have another one which talks about system of systems to system architecture. It has some notes on transitioning from a systems architecture to a systems architecture, and then goes into the afterword, the glossary, and bibliography about the authors, and then that's it. As a recap, we've got version 1's MagicGrid on the left, version 2's MagicGrid on the right. They're very similar except for the pillars are flip-flopped, behavior and structure. They added a new safety reliability pillar, which is at the very end of this text. You will create essentially 3 separate architectures. The problem domain architecture is separate from the solution domain architecture, which is separate from the implementation domain architecture. We talked about the configuration domain as well, and that is using the same blocks as the solution domain. So that is kind of the caveat there, is there is no configuration domain that you see in the grid, but it is essentially a revamped solution domain of decomposition. So it uses the same blocks from the solution domain. The problem domain is conceptual, the solution domain is logical, and the implementation domain is physical. Hope this helped.